So this is a video that's going to go through our last section for the semester while we're doing remote learning, and I just thought this was one of those things where it branches traditional physics with, it brings in the concepts of quantum physics, and there is a world of understanding that you could explore and try to really dig out. Lots of videos online. I'd encourage you to go and just search and look for things. Anyway, one of the things we're going to talk about are called Polaroids, which are a sheet, a type of material where light is going to be able to get through in a specific way by drawing parallel slits on this material. So now, first thing you need to understand is that light travels in a vibration as an electromagnetic wave. It looks a lot like a sine wave. Now it can be horizontally or vertically oriented like this one is. You got to imagine with me that this is horizontally oriented. Okay, imagine that that's side to side. Okay, and then it could also be at different angles. There's lots of different angles that light is randomly tweaked at. Now, as light sends its way down, we can create little sheets which have basically little slits in them drawn between lines. Okay, so we could think of it as a whole bunch of lines drawn like that on a sheet, right? So just imagine all these lines. And what it does is it allows light that's oriented in a specific direction or orientation to slip through the Polaroid and act like it's not there at all. Other light, if it's turned a different angle or different direction, is going to run into those solid lines and be reflected back or sent off in another direction or absorbed. Okay? And so we can sort of think of it as, let's see if I can find a good example. You guys have probably seen these with sunglasses before. And depending on the orientation of the light, we can use it to block out certain orientations. So the reason we do this is to think about it like if you're out fishing, okay? Water as it strikes the surface, or light as it strikes the surface of water. So let's put our water here, okay? Sunlight comes in, hits the surface of the water. We're going to learn about this. There's an actual angle that it comes in at. It's going to come, and there's going to be a big bright reflection off the surface. It's going to make it hard to see anything in that direction. And so we put on these sweet sunglasses, okay, that are Polaroids, that have polarized lenses. And what that's going to do is it's going to block the light that's being reflected off of the water at this angle, and that because it's all going to come off naturally polarized. And what that's going to allow us to do is allow us to get light from under the water where the fishies are. Yes, I said fishies. And we're going to be able to go and figure out what we're doing. Okay, this is similar with snowboarding. Having goggles where the glare off of the water or off of the snow isn't as bad. Baseball players will often wear these to try and prevent any glare off of different surfaces from keeping them in the outfield from seeing a ball or other things going on. And so as we look at these different Polaroids, hopefully you watched the demo where you saw that if you orient them at 90 degrees from each other, okay, you're going to block out all the light. But what happens when we start inserting other Polaroids, or what happens when they're not at 90 degrees? And we want to talk about how much light actually gets through. Let's take a look here real quick. I'm going to come in and do a quick demo. So the first thing you need to understand is that for a traditional Polaroid, the amount of light that gets through, so we're going to call this intensity, is equal to the initial intensity times the cosine squared of the angle of rotation between the two Polaroids. Now that's true after the first Polaroid. So let's talk about the general rules. First Polaroid, I'm just going to draw a little square here. We can kind of do it however. Okay, if you have, say, I naught right here, the initial amount of light coming into that first Polaroid, out of the first Polaroid, because it's going to knock out the half the light that isn't oriented the right way, again, this is statistically speaking, you're going to have 1/2 of your initial light coming through that first Polaroid. After that, okay, after that, if I put another Polaroid in here, okay, this angle of rotation, theta, that's where this formula steps in. So this is a really interesting thing because you have to understand this formula. The intensity that's going to come out will equal the intensity before this Polaroid, which turns out to only be half of the actual light that started the process. So we're going to call this 1/2 I naught from over there times cosine squared of theta. Now remember, when you put cosine squared of theta in the calculator, do cosine of theta and square it. Don't try to put the square in on theta or anything like that. It needs to be a separate afterthought. Okay. So let's take an example problem. Let's say that I have 3 Polaroids. Okay. And let's say that they're rotated 15 degrees. Okay. Each time 15 degrees and then 15 degrees more. And I just want to know what percentage of light gets through. This happens a lot. We actually don't measure the intensity of the light at the beginning. We just want a comparison. And so we're going to call this I naught. Now through the first Polaroid, we end up with half of I naught. Okay. It's always going to be smaller than that. Okay. Now to get through the next Polaroid, we're going to take 1/2 of I naught. That's from the previous one, right? This is the previous guy's amount of light times the cosine squared of 15. So let's go ahead and put this in the calculator and actually evaluate where we're at. Okay? Because this is going to have a specific value. I still don't know what I naught is, but I can figure out what's multiplied by I naught. What is cosine squared of 15 times 1/2? If we multiply all those things together, let's grab Desmos here real quick. First, we need to make sure that our mode is in degrees, which always switches back. But we want 0.5 times, we'll grab the function cosine of 15, close our parentheses, and then we want to put a parentheses right there and square. Now you might have been able to put the square on the parentheses after the cosine parenthesis was closed. I'm a big believer in just being careful. So I've got 0.4665. Let's go with that number. 0.4665. That is the percentage of light that still exists after the second Polaroid. Now to get to this Polaroid, we're going to take that amount, so I naught times 0.4665. That's just how much light there was originally, right? This is in the formula, that's the I naught. It's every time it's the one before. So we're taking the light from the one before, and we're going to times that by cosine squared of the angle of rotation, which was another 15 degrees. So I'm going to recalculate this, but instead of timesing by 0.5, I'm now going to times by 0.4665. So then my final I, or IF, I final, equals some amount of I naught. To figure out the amount, I need to multiply my numbers here. So I'm going to take this right up here, and listen, that number right there is 0.4665. So I'm just going to times by parentheses cosine 15 close parentheses squared. So I'm going to multiply yet again. Okay, and I get 0.435. If it would make it easier for you, one thing you can do is do the cosine of 15. Whoops. And then just square it. You could carry around this number 0.933. So you get 93.3% of the light from the previous one. And so in this problem, we end up with 0.435, back over here, equals 0.435 I naught. Or in other words, 43.5% of the light is going to get through that allows me to make some decisions about my expectations. The last thing that may or may not come in your homework, we just need to talk about it just in case it does, is the natural polarization of light off of a surface. For instance, when it comes off of the water, it naturally will polarize, okay? And so as the light polarizes off there, there is an angle above the horizon that's going to naturally happen at, okay, when it comes off of a smooth surface. And it's called Brewster's angle, okay? Now, let's be honest. Typically, when we're talking about this happening, the first material that the light is in is going to be air, okay? The second one is going to be the water or some other material, maybe glass, maybe the road, different things like that. And if we want to know what is the angle at which the light will come in and become polarized, okay, sorry, it's not above the horizon, it's a perpendicular, right? Still using Snell's law, if you will, but with tangent. If we want to know, hey, what angle is it going to bounce off here polarized and all organized in the same direction? And that's going to happen when the tangent of theta p equals n2 over n1. Now, when we look at that formula, tangent of theta p, the polarizing light, it will equal n2 over n1, where n2 and n1 are our indices of refraction. n1 for us on Earth is going to usually be air, which means that the tangent of theta p equals n2. Now, if we think about being on a lake, okay, on a lake where there's pretty calm water, okay, we're going to let n2 equal 1.33. So tangent theta p will equal 1.33. So let's go in and let's calculate that with Desmos. That would be a tan inverse of 1.33. That's 53.1 degrees. Okay. What this tells me, we said 53.1. Theta p is 53.1 degrees. So that tells me that when this is 53.1 degrees, or in other words, when this is 36.9 degrees above the horizon, when the sun is up here, okay, coming in, that the light is going to produce a really bright glare. And I'm definitely going to want sunglasses. There is a time of day when being out on the lake is super difficult. It's also a time of day when you're likely to get sunburned. And so knowing that rough time of day, those are things to think about and consider for when would you want to fly? When do you want to land an aircraft? When do you want to take off? Like, there are some bad scenarios where we don't want to be facing towards the sun. And so these are things that we can calculate and predict, and it's just awesome that we can do all of that. Watch the video or the demo video if you didn't already. It's really cool. And then if you have questions, come see me. But this is it, guys. This is the last section we're going to cover. I've had a great year. I wish we could be together more, but be healthy, be well, and let's have a great summer.